Hello guys, welcome back to my video, and in this video we will be talking about quantum gates. Quantum computers utilize the mysterious principles of quantum mechanics, superposition and entanglement to solve problems beyond the reach of a classical computer. Today we'll explore quantum gates, the essential building blocks that make the incredible power of quantum computing possible. Yeah, this is gonna be exciting. Let's talk about the introduction. What are quantum gates? Quantum gates are fundamental operations in quantum computing that manipulate qubits, analogous to logical gates in classical computing, but operate in qubits on superposition and entanglement. Why quantum gates matter? They are essential for the building blocks of algorithms that solve complex problems way faster than classical computers. They enable the unique capabilities of quantum computers, such as parallel processing and quantum interference. Just remember that quantum computers are only faster at some type of problems, not all. Types of quantum gates: single qubit gates like poly X gate, poly Y gate, poly Z gate, the Hadamard gate, and phase gates. There's also multi-qubit gates like CNOT gate, CZ gate, and Toffoli gate, used for entanglement and controlled operations. The key characteristics are that quantum gates are reversible, unlike most classical gates. They operate within the constraints of quantum mechanics, allowing the states to evolve based on probability amplitudes. The foundation for quantum algorithms, they serve as a building block for powerful quantum algorithms like Shor's algorithm and Grover's algorithm, showcasing the quantum computer's efficiency in solving problems. So now, before going into deep dive into different types of quantum gates, which is the main objective of this presentation, let's get brief about the inputs in classical computation. The basic unit is bits, which will be mutually exclusive. However, a quantum computation has a qubits, which can have multiple bits simultaneously, like this diagram right over here. So you can see that in the bits there can be 1 or 0. So 0, 1, 1 will just be 0, 1, 1. But in qubits, this is in a state where it can be 0 and 1, so it can be 0 or 1. So it could have all of these states just in one superposition. So it can store way more information. So these are the fundamentals to model and configure the quantum gate. It has direct bracket notation, Pauli's matrix notation, matrix multiplication, tensor multiplication, outer multiplication, Euler notation to model the phase of the phase and states of the qubits, and also the representation of multiple bits on the block sphere, and many other stuff. So, this is basically all the fundamentals that we are going to be talking about in a later video, not now. So, yeah. This is the typical Schrödinger wave equation, which you can solve to get the eigenfunction and eigenvalue. These values can be represented by the unitary matrix, and from here, quantum logic gate starts, which I'll be talking about today in this video. Wow! So now, I'll be talking about quantum to logic. Wow! So let me just get up. Okay, so now we will talk about quantum gates. So we have the I gate, which is called the identity gate. It is called that for a reason because it just makes the things stay the same, just like a classical buffer. Yep. Oops, I drew it a little bit wrong. So we got a triangle like that, just a classical buffer. And you can see the truth table right here. 0 gives 0, 1 gives 1. Yep. Now we also have it's also known as the X gate or the NOT gate, which just works as the classical NOT, just like this classical NOT gate or inverter gate. And this is the truth table. 0 becomes 1 and 1 becomes 0. Just how it is in classical. The I gate, it doesn't do any rotation to the block sphere representation, but it doesn't do any meaningful rotation, so it doesn't really do anything technically. And the Y gate actually almost works like an X gate, but it also brings in another factor, which I'll be talking about later. So now let's talk about the Z, S, and T gate. All of these gates turn the block sphere representation in the z-axis, but they just do it in different angles. So only problem is it doesn't do any meaningful rotation. So even if it was here, it would just turn it like this, and it wouldn't affect the superposition in any meaningful way. You'll still get the graph as the same thing. So now I'll be talking about these two gates, and these three gates actually. So this is called the square root of NOT gate. And I made that look, think that looks weird, but basically if you have two of these, you will just get a NOT gate. So you'll just get a NOT gate. Oops. You will just get a NOT gate. This is how to draw a NOT gate, or you can also draw it like this. Whatever way you want. You can draw it in whatever way you want. So that's it. It may look weird, and I think it sort of does for everybody, but it's basically just quantum mechanical. That's how it works. It's just half of the regular rotation that a Pauli X gate does. So this is called a Hadamard gate. This, if you have it on 0 or 1, it will change it to a superposition where the value of 1, it will come 50% of the time, and the value of 0 will collapse to 50% of the time. Where you can see the output state here. I'll be talking about that in a different video. And this is called a general phase gate. This is a gate which doesn't do any meaningful rotation, just like Arham. So yeah. Now I'll be talking about controlled quantum gates. These are controlled quantum gates. Basically, I'll be showing you how it works. This is the C-NOT gate. So it may look a little bit weird, but it's just the NOT gate. This is the NOT gate, and this is a line, and there's a control qubit. So this is called a control qubit, this is called a target qubit. So now, what will happen if this is 1 and it goes into the control? It says, hey, I'm 1, so you have to do your thing. So when it's 1, it just wakes up the NOT gate, like as you can just say, it sort of wakes up the NOT gate, and the NOT gate does an operation. It does its operation. But if it's 0 and this is like 1, even if 0 goes into here, nothing happens, and the NOT gate is still sleeping and it forgets to do its operation, so it just leaves it as 1. And this will always continue to be the same qubit. So that's just an analogy, that's technically how it sort of works. So this has a very similar behavior to an XOR gate. But you may be saying, hey, an XOR gate only has one output. This has 2. So what do you have to do there? You have to modify a little bit. You just need to take one of the first outputs and drag it up. So this is what happens. If this is X, this will stay as X. And this is Y. This is the symbol for XC, not Y. I mean X XOR Y. X, this plus thing is XOR Y. And the same thing happens here. X, Y, same thing happens, X, and here X, XOR Y. That's exactly what happens. So now all of these other gates work in a similar way. If it goes here, it wakes it up and it does its operation. Otherwise, it doesn't. So now we will be talking about the classical gates in quantum representation. So let me just sit back right down. So now let's talk about classical gates in quantum representation, just like these. So right behind me is the AND gate right here, the OR gate right here, the AO gate right here, and I will be, instead of demonstrating it here, I'll be demonstrating it in a tool called Qiskit. It's basically based on GitHub library. I have modified it a little bit. I'll be sharing that modified version in the card up there or up there. I forgot where, but it'll be shared in the card. So see, you can see the GitHub representation. So this is Qiskit. This is a open source tool on GitHub. So yep, here it is. This is the I've put a few programs in here in the QI section. This was the original stuff, but I'll only be talking about some of these. So this is the AND gate. So we will be using a thing called quantum parallelism in Qiskit, which I'll be talking about when I get to it. So first, let's see what the AND gate looks like. There's a quantum gate. This is what an AND gate looks like in quantum. It is also called a Toffoli gate. It may look similar to the C0 gate, but remember, there's two controlled now. So only if both of them are on, then only it'll wake the poly X gate up. So see, this is that gate. Now I will be showing quantum parallelism. How it works is all I have to do is put a poly H gate on both of the input qubits. So whatever there's the input qubit, you just have to put the poly X gate. So see, now all I have to do is just copy this like so. Control C, Control V. Now all I have to do is put in the input gates, the input qubits, and I can see it has put in the input right here. Now let's see what happens after the after the AND gate. So this is after the AND gate. Put the AND gate on it. So because of quantum parallelism, we have to generate the truth table by just putting two X gates. So this histogram just shows the truth table. Here I will be showing. So this is 0, but the last one right here is the so this last qubit right here is the output, and the other two qubits are the inputs. So see, if there's 0 and if there's two zeros, it'll be 0. If there's 0 1, it'll be 0 1 0. If like 0 1 is 0, 1 0 is 0, and if it's 1 1, then it'll be 1. Just how an AND gate works. So yeah. Now we're going to be talking about an OR gate. OR. The OR gate is not just one quantum gate, it is actually two. So first I'll show it. Right around here. Hey, move around. Where is the OR gate? Yes. This is the OR gate. It's comprised of many gates. It's not just one singular gate. Because in an OR gate, you're technically destroying information if you do it in one step. So you have to save the inputs. That's how it works in an OR gate. So let's use quantum parallelism. So So now I have put the edge gates on both of the input qubits right here. And now let's go to the output. So this is the circuit representation. You just put two edge gates. So now quantum parallelism will work. And here you can see the outputs. So you can see this is the output, this is the inputs, 0 0 0 0 1. So this is one of them is 1, the 1 1 0 1 1 1 1. Yeah. Quantum parallelism, that's the advantage. Wow. Haha. Okay. Now we have done OR and AND. Now there's also an AO gate, which I have already done quantum parallelism. It is pretty lengthy, but it will work. See, this is it. Next, I'll be showing you the half adder and the AO, a little bit more detailed. And I'll show up to the board and explain it. So this is the HA and AO. I'll just be standing up and explain it. Okay, yes. So this is the this is the H8 half adder. So first, this H gates are used for quantum parallelism, which I described. So we don't need this right now, as we're just checking the quantum algorithm and the classical algorithm. So now in the input, let's just do 1, 1 for now. So as we remember, 1 is going into the control, it wakes the operation up. So these two always have to be 0 as helper qubits. So this 1 goes in here. Now it goes into the CNOT gate, which applies the operation, which from 0 it turns into 1. Everything else remains the same. Now it does this again. So it does 1, 1, and then this goes 0 because it wakes it up, it does the operation again. So if you do NOT of 1, you just get 0 again. So this still stays the same. And now since both of these are 1, it does an AND gate. So both of these are on, so it wakes this up. If only one of them was on, it would not. So the sum is 0 and carry is 1. Now let's try it on the classical algorithm. So 1, 1, 1 goes in there, this becomes AND, this 1, it goes into XOR, it does a 0. So carry is 1, sum is 0. We were correct, yay! And we can also see with the truth table made by the histogram, which is made by the quantum parallelism, right here. And we put a 1, 1, we got 0, 1, so we were correct. Now let's try it on the AO, which is a little bit more complex, but it's not that much complex. So let's get rid of these pesky edge gates, which we don't need right now. And let's just put a 1, 0, 1. First, let's see what is there on the truth table. So 1, 0, 1, it is saying it should be 1. Let's check if that's true. So this X line X gate is called a swap gate. It just swaps the superposition up and down and up and down and up. Yeah, so it just swaps the superposition. These two helper gates should be 0. So let's see what happens. First, this swaps 0, 1. I'll make like a grid of numbers right here. So see, and then 1. Since both of these are not on, it's the CNOT gate is still sleeping. Nothing happens here. And now the 1 goes in here, it wakes up the gate. So it just becomes 1 now. Now since this cannot wake it up, nothing happens here. And since these two are not on, it cannot wake it up. And now these two get swapped again. This qubit number 3, if we cannot destroy quantum information, we had to add it as the intermediate step right here. So we will also be checking that, even though I did not measure it. This line thing is called measurement gate. It just measures it into a 0 or a 1. So let's see what happens. So we got the answer output as 1 and the intermediate step is 0. Now let's see what happens here. 1, 0, 1. 0, 1 goes in here, it becomes 0. 1 goes in here, it becomes 1. So 0 is the intermediate step and 1 is the intermediate. And 1 is the final output, which we also got from here because of quantum parallelism. So yay, we were right. So now we will be checking out what is quantum parallelism, which I've been talking about for so long. And I've been wondering, what do you mean is it actually? So this is what quantum parallelism is. It, as I said before, it can generate the truth table on one singular run, which a classical computer cannot. And there's many quantum algorithms like the Deutsch algorithm and Deutsch-Jones algorithm. So these two algorithms I'll be talking about in the next videos. And that's all. Okay, bye-bye.